Hi, everybody. Welcome to Lecture 5 of Electrical Engineering 331. In this lecture, we will be reviewing some ideas about differential equations. Now, in this lecture, we're going to concentrate on second-order differential equations with constant coefficients. But the techniques we will discuss the technique we will discuss is more generally applicable. It's amazing how often in physics and engineering you will encounter second order differential equations. Laplace's equation in one dimension is second order. Poisson's equation, again in 1D, is second order. The wave equation in 1D is a second order equation. So all of those are in 1D are ordinary differential equations, just like the ones that we will be dealing with. And certainly in this course, we will repeatedly look at second order differential equations with constant coefficients. So this is something very useful to look at, and today I hope everything I'm going to talk about is review. In other words, I hope it's all something that you have seen before, but if not, that's okay, because I think you'll find this pretty straightforward. Now, so let's just jump right in. Every differential equation we're going to look at, once again, it's going to be, first of all, it's going to be ordinary differential equations, which means that you don't see any partial derivatives here. And it's going to be second order, which means that the highest derivative present is going to be the second derivative. And it's going to have constant coefficients, just like we see here. The coefficient here is 1, and then 5, and 6. And furthermore, actually, we can say one more thing. Everything we're going to talk about in this lecture, they will all be homogeneous differential equations, which means that we have 0 on the right-hand side. Later, we will talk about what to do when we don't have 0 on the right-hand side. But for right now, we're just looking at these homogeneous equations. So you're going to find out that I'm going to cover a fair amount of material here in this lecture because it is our review. At first, I'm going to go very, very slowly, covering every little detail, but after we've done it a few times, I think we'll be able to go more quickly. So whenever you have differential equation of this type, it's going to be useful to begin by proposing a solution of the form y of t equals ce to the pt. We're basically just guessing that is going to work. And in fact, with equations of this type, this will always be useful. So in order to substitute that now for y, we're going to need to know, well, what's dy dt and what's d squared y dt squared. So let's go ahead and compute those. If y of t is equal to ce to the pt, then dy dt will be pce to the pt, because remember, c is a constant, so when we differentiate, that has no effect, but when we differentiate e to the pt, we get this p. And then when we take the derivative again, we'll get another p. So we get p squared ce to the pt. Then if we substitute that for the second derivative and pce to the pt for the first derivative, and don't forget the 5, and then substitute ce to the pt for y of t, and don't forget the 6, and then bring down the 0, we will get this. Now, looking at this equation, if we factor out ce to the pt from every term, then we see that equation can be written like this. And so for this equation to be true, either p squared plus 5p plus 6 is equal to 0, or ce to the pt is equal to 0. Now let's think about this for a moment. ce to the pt here, this ce to the pt, well, that's y. And so, yeah, sure, if y equals 0 would indeed make this equation work, but that's what people call the trivial solution. That's almost never the solution that we're looking for. We're looking for the non-trivial, the non-zero solution. So we come back down here and we're going to reject this possibility. We're not going to worry about ce to the pt is equal to 0. And so therefore, we're left with the conclusion that it must be true that p squared plus 5p plus 6 is equal to 0. Now look at this equation we have arrived at. This equation, p squared plus 5p plus 6 equals 0, it looks a lot like what we started with up here. D squared y dt squared plus 5 dy dt plus 6y is equal to 0. It looks a lot like it, and that's important to realize because after we've done this a few times, we're going to want to just jump immediately from the differential equation down to an equation of this form. But notice, you see now why we would want to use this technique of proposing y of t equals ce to the pt, because it has allowed us to go from something pretty complicated, a second order differential equation, to just a simple algebraic equation down here. It's a algebraic equation of degree 2. So that's certainly a big step forward. But let's see now how we finish the problem. Okay, so we see it doesn't take too much insight to see that this equation can be factored like this, as p plus 3 times p plus 4 is equal to 0, and therefore p is either equal to -2 or -3. Those are the possible values for p that will make this work. Now remember, what we proposed up here was y is equal to ce to the pt, and so since we have two possible values for p, we have -2 and -3, then we'll have two terms here in the solution. Y of t equals c1 e to the -2t plus c2 e to the -3t. And you should not be surprised at all that we have two solutions, because this is a second order differential equation. If it were a third order differential equation, we'd have three terms. A fourth order differential equation would have four terms. First order would have just one term. Okay. So now that we have this solution, now this is our final solution at this point. We cannot determine anything about C1 and C2 because we don't have any boundary conditions. All we have is a homogeneous differential equation. So this is the final solution. But in each problem that I'm going to do, I have provided a check just to convince you that it is correct. And so now in these checks, they get sort of tedious, so I won't cover, after the first couple or so, I won't cover every detail. But at the beginning, let's just go ahead and try to do it pretty thoroughly. So remember now, our original equation was d squared y dt squared plus 5 dy dt plus 6y is equal to 0. So what I've done here in this checking procedure is I have simply substituted this expression, c1 e to the minus 2t plus c2 e to the minus 3t for y here in the second derivative term, and also in the first derivative term, and also in the term involving just y. And over here on the right, I put 0, and I'm putting a question mark over the equal sign because I don't know if they're equal yet. I'm hoping they are. If this is, remember, I'm checking. And if we've done the problem correctly, then the left-hand side will indeed be equal to 0. But if we've done it incorrectly, then we won't get 0. So keeping my fingers crossed. But it's good to put the question mark over the equal sign just to help you remember that you don't know that they're equal. You're trying to verify that they're equal. Okay, so let's see how this will go. When we take the second derivative of c1 e to the minus 2t, we know we take the first derivative and a negative 2 will come out front, and then we take the derivative again and another negative 2 will come out front. So we get negative 2 squared c1 e to the minus 2t. Similarly, when we differentiate this second term twice, we'll get a negative 3 popping out in the front twice. So we get negative 3 squared times c2 e to the minus 3t. Then we have 5 ddt of this, and so when we take this derivative, a negative 2 will come out. So we have 5 times negative 2 c1 e to the negative 2t. And then when we differentiate this one, a negative 3 will come out front. So we have 5 times negative 3 c2 e to the minus 3t. And then finally, we just write down, go ahead and multiply out the 6 for the last term. So we have 6 c1 e to the minus 2t plus 6 c2 e to the minus 3t. Now, we can, in going from this line to the second line, I've just really all I've done is written down negative 2 squared is 4, and negative 3 squared is 9, and 5 times negative 2 is negative 10, 5 times negative 3 is negative 15. That's really all I've done there. And now, in going from this line at top to the next line, what I've just done is group together all the terms involving c1 e to the minus 2t and all the terms involving c2 e to the minus 3t. And so for the c1 terms, you see I get a 4 there and a negative 10 and a 6. And then for the c2 terms, I have 9 and negative 15 and 6. And so when I group them like that, I'll get this term, or this equation. And of course, 4 minus 10 is negative 6 plus 6, so I get 0 there. 9 minus 15 is negative 6 plus 6, 0 there. So I have 0 plus 0 question mark equals 0. And of course, that's true. And therefore, we did indeed reach a correct solution here. So this is the solution to the first differential equation we're looking at today. This differential equation up here. Okay. So this is what happens when your differential equation or when the algebraic equation associated with the differential equation has two real non-zero roots. And now we're going to look at some of the other possibilities that can arise. So, example 2. Okay, again, just as we are going to do over and over and over, again, we will propose a solution of the form y is equal to ce to the pt. And since we want to be able to substitute into that equation, then we want to find out what the first and second derivatives are. And just as before, when we take one derivative, one p drops out, pops out in front. When we take a second derivative, another p pops out in front. So we have this. Again, we will substitute those back into the differential equation. And when we do, we will get p squared ce to the pt plus 16p ce to the pt is equal to 0. And just as before, we will then group terms like this. And so now our algebraic equation will be p squared plus 16p equals 0. And the other possibility is ce to the pt is equal to 0. This corresponds to the trivial solution, so we reject that. So we get p squared plus 16p equals 0. And once again, I encourage you to compare this equation with what we started with. And so you can see the second derivative becomes p squared, the first derivative becomes p. So we get p squared plus 16p equals 0. Right there. Okay, So if we factor out a p, that just gives us p times p plus 16 is equal to 0. And so the two possible roots this time are p equals 0 and p equals minus 16. So the only difference here is that we still have two real roots, but now one of those roots is equal to 0. And I just wanted to remind you that when you have a root of 0, then that will become a constant. It's just simply a constant. So we have y of t is equal to c1 plus c2 e to the minus 16t. This is our solution in this case. Once again, we can substitute that back into the differential equation, d squared y dt squared plus 16 dy dt, and see if that really does give us 0. And let's see how it will go. When we take the second derivative of a constant, we get 0. So we don't have to worry about that term. When we take the second derivative of c2 e to the minus 16t, well, minus 16 will pop out twice because it's two derivatives. So we have a minus 16 quantity squared times c2 e to the minus 16t plus, and then this 16 comes down there. And then when we take one derivative, take the derivative of c1, the derivative of a constant is equal to 0, so we don't have to worry about that. And the derivative of c2 e to the minus 16t, we get a minus 16 popping out right there, and then c2 e to the minus 16t, and that equals question mark 0. So we get 256 c2 e to the minus 16t minus 256 c2 e to the minus 16t, and so sure enough, 0 is equal to 0. So that's correct. So we conclude then that this expression is indeed the correct solution. Now let's go to another possibility. D squared y dt squared plus 8 dy dt plus 16y is equal to 0. Now that we've seen this procedure twice, I hope that you will agree that when we propose the solution of the forms y of t equals ce to the pt, we're going to conclude this. Again, as before, d squared y dt squared becomes p squared, dy dt becomes p, so we're going to have p squared plus 8p plus 16 equals 0. And now this gives us p plus 4 times p plus 4 is equal to 0, or p equals negative 4 and negative 4. So what makes this example different is that we have repeated roots. In both of the previous examples, our two roots were what they call distinct roots. In other words, they were different from each other. But now we have repeated roots. So the first p equals negative 4, that's easy. That corresponds to y of t equals c1 e to the minus 4t. But when it gets repeated, then what we have to do is we write down again a c, we'll make it c2 e to the minus 4t, but then we have to multiply that by t. If we had a third order differential equation and we had p equals negative 4 3 times, if it were a root of order 3, then our solution down here would be c1 e to the minus 4t plus c2t e to the minus 4t plus c3t squared e to the minus 4t. But of course, we just have second order here, so this is what you do. So just remember that when you have a repeated root, then you're going to have to, for one of the solutions, you're going to have to multiply by t. Okay, and so we can check this, and again, our original equation was d squared y. This is taking the role of y, or taking the place of y. So d squared y dt squared plus 8 dy dt plus 16y equals question mark 0. And now this one, the checking procedure gets a little bit ugly because when you take the derivatives of terms C2t e to the minus 4t, you have to use the product rule. So I'll go through this one a little bit more carefully. So let's see how this will go. Okay, if we take the second derivative of c1 e to the minus 4t, that's the minus 4 will pop out twice, and so we'll have minus 4 quantity squared c1 e to the minus 4t. Now, for the second derivative of this, we can't do that all at one time because of the presence of this t. So I'll write this, what I'll do is the following. Okay, the second derivative operating on that, okay, C2 is a constant, so it can come out front. And I can write the second derivative as the first derivative of the first derivative. So what's in the brackets here is the first derivative of t e to the minus 4t. And you can see I get the first term, t, times the derivative of the second, so minus 4 e to the minus 4t, plus the second term, e to the minus 4t, times the derivative of the first term, t. The derivative of t is just 1. So this bracketed term right here represents the first derivative of t e to the minus 4t, and then I still have one derivative left out here in front of the brackets because this is second derivative there. Okay, so now I go to this term, and the derivative of c1 e to the minus 4t is minus 4 c1 e to the minus 4t, and I bring down the 8. And then for the derivative of this, c2 can come out front, and here's my 8. So here's the 8 coming down here, and the c2, the derivative will come inside the c2, so I'm going to write down c2, and then what's left is the derivative, and we've already calculated the derivative of that term here, so we just have the same thing. Notice that this bracketed term and this bracketed term are exactly the same. And then we'll have 16c1 e to the minus 4t there, and 16c2t e to the minus 4t there. And so now this first term, minus 4 squared is 16, so that's easy. And then for this second term, we bring down the c2, and now we have to differentiate this term with respect to t. So again, we'll have to use the product rule on this first term, and the minus 4t, I bring that down, minus 4t, I'm regarding that as the first term. So we have the first term times the derivative of the second term. The derivative of the second term is e to the minus 4t, so the derivative of that is minus 4 e to the minus 4t. So this is the first times the derivative of the second, and then we have the second, e to the minus 4t, times the derivative of the first, and the first term is minus 4t, so the derivative is minus 4. And then we also have to take the derivative of this, of e to the minus 4t, which will be minus 4 e to the minus 4t. Then we have 8 times negative 4, so that's negative 32 c1 e to the minus 4t. And here we would have 8c2 times minus 4t e to the minus 4t to give us this term here. And then 8c2 e to the minus 4t, and then we bring down the last two terms. And so finally, then when we group all the terms involving c1 e to the minus 4t together, and all the terms involving c2 e to the minus 4t together, we'll get, okay, the first one gives us this 16, and then the next one, here we have 16t times c2 e to the minus 4t, so that's right there. And then these two terms together, these two can be combined. We got a minus 4 and a minus 4, so minus 8, and that's right there. And then this one, minus 32 to c1, so here's the minus 32. And here's minus 32c2, so that's minus 32t times c2. So that's right there. And then here's 8c2, so that's right there. 16c1 is right here. And 16 t C2 is right here. So that's what we get when we group all of this together. And then we see that 16 minus 32 is negative 16 and 16, so we get 0 there. And here 16t minus 32t is negative 16t, plus 16t is 0, and negative 8 and 8 is 0. So we have 0 plus 0 equals question mark 0. And so sure enough, after all the smoke has cleared, we do get 0, and we conclude that this right here is indeed the correct solution to this differential equation. So again, this is the kind of thing that happens when you have a repeated root. And this next one is a very simple repeated root problem. This is example 4. D squared y dt squared is equal to 0. And so again, we propose a solution in the form y of t equals ce to the pt, and we know then from experience this this differential equation, when we make that substitute or that proposal, this becomes just p squared equals 0. And so the first 0 corresponds to constant, and then the second will, by using the principle that we used in example 3, when you have a repeated root of 0, then you have to, when you have a repeated root, then you will take the form of the first solution and multiply it by t. So here we have a constant, and here we have a constant times t. And so this is the solution to this differential equation. And when we check it, okay, d squared y dt squared, so d squared y dt squared equals question mark 0. When we take the second derivative of c1, we get 0. When we take the second derivative when we take the second derivative, okay, let me start over. I'm rewriting the second derivative here as the derivative of the first derivative. Okay, so when I take, I'm pulling one derivative down, and then the other derivative I'm going to hit operating on this. Okay, the first derivative of a constant is 0. And the first derivative of c2t is c2. Now I need to take one more derivative. The derivative of 0 is 0. The derivative of a constant is 0. So I get 0 equals 0. And that checks. So this is indeed correct. And now we have just 2 more examples to do. So the 5th example is d squared y dt squared plus 9y of t equals 0. And once again, we will propose a solution in the form ce to the pt. So this gives us p squared plus 9 is equal to 0, which means that p squared is equal to negative 9. And so this is, you have this unusual situation. How can you square something and get a negative number? And so we now have imaginary roots. So that's what makes example 5 different, is that in examples 1 through 4, all of our roots were real, but now we have imaginary roots, and the roots are 3j and minus 3j. When you did this kind of problem in math, you probably would have written it as 3i and minus 3i, but in electrical engineering, we usually use j instead of I. So 3j and negative 3j, where j is the square root of negative 1. Now, if you wanted to follow exactly the format that you have had for the previous problems, then you would write, okay, this means then that the solution is y of t equals c1e to the 3jt plus c2e to the minus 3jt. And that is correct, but we very frequently will decide to write it in a different form. And that different form is this: d1 sine to the 3t plus d2 cosine to the 3t. Now, we will see later why these two expressions are the same. It has to do with something called the Euler formulas. But just remember that when you have imaginary roots, you will usually go to the trig functions. And as I have this remark here, actually, to be honest, rather than writing it as d1 sine of 3t plus d2 cosine 3t, you would probably still write down c1 and c2, but it's important to realize that the c1 and c2, if you did write it as c1 and c2 here, that those c1 and c2s would not be the same as the c1 and c2 up here. Now, it doesn't really matter because at this point, c1 and c2 are arbitrary constants anyway, but if to show the equivalence of these two solutions, we would, or if we tried to do that, we would see that that actually these constants down here are different from the ones up there. But we'll save that for later when we study the what's called the Euler formulas. Okay. So we have this solution right here, y of t equals d1 sine 3t plus d2 cosine 3t. And as usual, then we will check. So d squared y dt squared plus 9y, is that indeed equal to 0? Okay, and let's see. So I'm going to write the second derivative as the derivative of the first derivative. When I take one derivative of this, I'll get 3d1 cosine 3t. And then the derivative of cosine is minus sine, so I'll get minus 3d2 sine 3t. And here just come down 9d1 sine 3t and 9d2 cosine 3t. And equals question mark 0. Now I'll take one more derivative, and so 3 comes out front, and derivative of cosine is negative sine, so I'll get minus 9d1 sine 3t. And then here, when I take the derivative of the sine, the 3 comes out front and I get cosine, so minus 9d2 cosine 3t plus 9d1 sine 3t plus 9d2 cosine 3t. And you see that everything on the left-hand side cancels, and we get 0 equals 0. So indeed, that works. And indeed, this is a correct way of writing the solution for the differential equation. And now we have one last example to do. And that will be d squared y dt squared plus 6 dy dt plus 10y equals 0. As usual, we propose y of t equals ce to the pt. And so this differential equation corresponds to this algebraic equation. Now this time, at least to me, it's not so clear how to factor this. And so when you don't know how to factor a quadratic equation, you can always use the quadratic formula. So that's what I have done here. P is equal to negative b. B is the coefficient of the first order term. So this is negative b plus or minus the square root of b squared minus 4ac over 2a. And so this becomes negative 2 plus or minus the square root of 4 minus 40 over 2. Which is negative 2 plus or minus the square root of negative 36 over 2. And so this is negative 2 plus or minus 6 times the square root of negative 1 over 2, or negative 6 plus or minus 6j over 2. Then divide everything by 2, and so we get these two roots here. P equals negative 1 plus 3j, P equals negative 1 minus 3j. So this is the final case. This case is complex conjugate roots. Now, in the previous case, they were complex conjugate too, but the real part was 0. But now the real part is not 0, it's equal to negative 1. So we have this more complicated situation here. And so let's go ahead and write this down just as you would expect. You have C1 times minus 1 plus 3jt plus C2 times minus 1 minus 3jt. And that could be written as C1 e to the minus t e to the 3jt plus C2 e to the minus t e to the minus 3jt. And then we could factor out an e to the minus t since it's in common to both of them, and we'd be left with C1 e to the 3jt plus C2 e to the minus 3jt. But as we saw in example 5, or as we said in example 5, frequently instead of having C1 e to the 3jt plus C2 e to the minus 3jt, we will instead write it like d1 sine 3t plus d2 cosine 3t. So we'll do that here as well. And now if we multiply through by e to the minus t, then we have this way of writing y of t. So we have one solution that is e to the minus t sine 3t, another solution that is e to the minus t cosine 3t. And the checking procedure, we've been through this over and over now. I mean, this one is going to be ugly because each one of these terms is a product, and so every time we differentiate it, we'll have to use the product rule. So I'll just say I will leave it to you if you want to see the details there. I'll just very briefly go over it. So this is d squared y dt squared plus 2 dy dt plus 10y equals question mark 0. And so when I expand all of this out, I'm going to rewrite the second derivative as the derivative of the first derivative. So this bracketed term right here represents the first derivative of this. And then I just brought down this term to right here, and brought down this last term to right there. Okay, and I've put this little squiggly mark to help us remember this is all just one equation. Okay. Then what I've did in going from here down to here is, since this is a derivative of this, and this is the derivative of twice this 2, I can take the 2 on the inside. I just group all this together. So I have the derivative here. So see, here's 3d1. So this term comes down right there. This term comes down right here. And let's see. Oh, wait, I think I'm doing this a little too quickly. Okay. This term right here, the first term up here, does indeed come down here. But then this next term will combine with 2 times this term. See, this is negative d1 there, but it becomes positive d1 there because we have negative d1 and then this 2 times positive d1. So that's how we get a positive d1 e to the minus t sine 3t there. And then this term comes down directly, but this term, the minus d2, and then we have plus 2d2, so that's how we get plus d2 e to the minus t cosine 3t there. You don't have to do it this way. This is just me trying to make things a little bit easier because it's really, this is a pretty tedious problem. So I get, and then I just bring this down here for the second line. Now, finally, I have to go ahead and use the product rule in calculating the derivative of each one of these terms, and I'll let you, if you want to, verify that everything here has been done correctly. Notice that now it takes 3 lines to write out everything. But after I do that, then a lot of stuff, what I do is I will group things together. I'll group together everything involving d1 e to the minus t and everything involving d2 e to the minus t. And still on the right hand side I have equals question mark 0, but if you look carefully you will see that everything there cancels out, and so I'll get in the end, sure enough, 0 plus 0 equals question mark 0, and that does check. And so therefore we conclude that this really is the correct form, or the correct solution, one way of writing the solution for this differential equation. So that covers I think pretty much everything that can happen when we have a second order ordinary differential equation with homogeneous differential equation with constant coefficients. And if you be sure to look at this, it will be definitely helpful in doing test 5, and this is something that we will need repeatedly in doing some problems that we will face very soon. So good luck, and I will talk to you soon.